Okay, so what happens is we already talked about ionic compounds properties last week. They have high melting point and they can conduct electricity, but only when it's in molten or dissolved in water, called aqueous, but cannot conduct when it's in solid. And then we learn why. Okay, we talked about why. It cannot conduct because in solid the ions are not moving, in molten the ions are moving. Okay, can? Now, HCl is a covalent. So now we're going to talk about why. What can they do? So remember, they are simple molecules. So they have a low melting point and boiling point. Okay, so in room temperature, they exist as gases usually, sometimes liquid lah. Very rarely we will have solid covalent unless you freeze it. Okay, so when the molecules increase in size, the melting point and boiling point increase, and they have poor electrical conductivity. They do not conduct electricity. Okay, so we need to know why. Okay, we need to know why. So because they have small molecules. Okay, so this is HCl. This is another HCl. So this molecule and this molecule is just two separate molecules. Okay. Boiling point means you separate the molecules. Now, please remember, a lot of students make this mistake. They will say ionic compound has high melting point because ionic bond is strong. Covalent molecules has low melting point because covalent bond is weak. No, that's incorrect. Covalent bonds are actually very, very strong. Okay, covalent bonds are very, very strong. In fact, a covalent bond is stronger than an ionic bond. The reason why the melting point and boiling point is low is because when we melt or boil it, we don't separate. This strong covalent bond is not separated. The one we separate is here, the intermolecular forces of attraction. Okay, so the one we separate is here. This is called intermolecular forces of attraction. Okay, intermolecular. So this is intermolecular. Can you draw this so that you know what it is? Draw it next to the intermolecular. Okay. Okay, done. So because the intermolecular forces of attraction are very weak, it is very easy to separate them. Okay, so you cannot separate the inside. So I want you to imagine as two people are holding hands. When I separate them, I separate the two people, right? I don't separate the hand from the socket, right? I don't separate the person's head from the body, right? Okay, so inside the person is covalent, in between is intermolecular. Okay, so intermolecular is exactly like gravity. The bigger it is, the heavier the gravity, right or not? So, for example, Earth to the Sun and Earth to the Moon, of course, Earth to the Sun, the gravity is stronger. So, when you have different molecule size, the bigger the size of the molecule, the heavier the molecule, the higher the melting point and boiling point as comparison. Okay, so they have very low melting point because it's only very weak intermolecular forces of attraction between the molecules. All right. But when the size of the forces increase, the size of the molecules increase, the forces also increase. So this is very, very simple in terms of in group 7. Remember group 7, there's fluorine, chlorine, bromine, iodine. They are all molecules. They're all molecules. But as you go down, the size becomes bigger and bigger and bigger. So what happens is when you go down, their melting point and boiling point also becomes higher and higher and higher because the size of the molecule is bigger. So, for example, fluorine, the molecule size is so small. So, because that between this fluorine and this fluorine, it's very weak forces of attraction. But iodine, the molecule is really big. So, between this iodine and another iodine, it's very strong. So iodine is a covalent molecule, but it exists as solid at room temperature because the size of the molecule is so big. Okay? Okay? So the bigger it is, the bigger the melting and boiling point. All right? So it also cannot conduct electricity. Okay, why cannot conduct electricity? Remember I told you about who can conduct electricity? Something must be moving, right? So ions must be moving, electrons must be moving. But in a covalent molecule, it is just simple molecules. So simple molecules have no charge. So because they have no charge, no ions and no electrons. Okay, no ions and no free moving electrons. So there's nobody to conduct electricity. Okay, you cannot say they have no electrons. They have no free electrons. There's a difference. Okay, there's no free electrons because do they have electrons? Of course, they have electrons. Okay, they have electrons. Can? All right. So what happens is, uh, these compounds, if they are in solid, they cannot conduct electricity, so we use as insulators like rubber, wood, okay, plastic, they're all covalent. So we use as insulators. Okay? Okay. Easy, right? Okay, so covalent, very easy, only, very simple. The properties you learn now is very, very simple. Okay? All right. Today we learn this last part of chapter 2. This is the last part of chapter 2. After this, we are going to stop chem. Oh, got two more parts. After this, we're going to stop chem and then we're going to go to bio first. Okay? Okay? Okay, so we learn around it because I don't know what your teacher is going to do in school. I don't know whether they're going to do chem, bio, physics, or just chem, bio, bio. So I don't know. So we just uh, make sure we do everything lah. Okay. So diamond and graphite and metallic bonding, the last part. Okay. So first of all, diamond and graphite also covalent. But covalent, there are two types. They are simple molecular, like I taught you, and now this one is called giant covalent structures. Okay. Okay. These are called giant covalent structures. All right. Ready? Okay. So diamond and graphite has a very specific structure. Okay, I don't know whether your teacher's going to make you draw, but it's actually part of your syllabus. Okay, so if your teacher's going to make you draw, make sure you know how to draw. I don't think they're going to make you draw the whole thing. Usually for this chapter to draw is usually ionic and covalent. Okay, okay. So structure and of graphite and diamond. Okay, so uh, do you remember what is methane? Do you remember? We learned this last week. Do you remember? Okay, never mind. So methane is CH4, right? Okay. So CH4 is like this. Remember we taught you how to draw this? Okay, so carbon obviously has four bonds. Okay, and it is bonded to hydrogen. Each hydrogen, how many bond? Each hydrogen, one bond. Okay, so carbon has four bonds. Hydrogen has one bond each. So the thing is, once they finish this, they stop. Okay, does this hydrogen go and bond with another carbon or another hydrogen? No, cannot. Because hydrogen bond with this, then finish. The only thing that you can have between this molecule and this molecule, for example, is the intermolecular forces of attraction. This hydrogen cannot go and have a covalent bond with this hydrogen, right? Okay, so it only has intermolecular. But giant structure is slightly different. Giant structure is like this. Each carbon atom in graphite is bonded to three others. So, like this. This is how graphite looks like. This carbon, okay, I cannot draw here after you get confused. Okay, okay. So this is a carbon. This carbon, if you notice, this carbon is connected to, okay, this carbon is connected to three other carbons. Teacher, only two. Got lah, got another one. Okay, so it's easier to see with the one in the middle. Okay, so this one, for example, this carbon. This carbon is connected to three. Can see it? One, two, three. This carbon is actually also connected to three. Is one. This carbon is one, two, and then another one is on the other side lah. Because it goes on and on and on. Okay, and then this carbon is also connected to three. One, two, and then another one in front. Okay, so if you look at the shape, this is a hexagon, right? So they say that each carbon atom forms three covalent bonds with three other carbon atoms, and it forms a hexagonal layer. Okay, how long does this layer go? It doesn't just stop here. It goes on and on and on for a few million atoms. Get it? So it's a one big layer. It goes on and on and on. So because it's one big giant layer, that whole layer is called one giant molecule. Okay? So only three is used for bonding. The other one forms a free electron that moves around. Okay, so that's why graphite is the only non-metal that can conduct electricity. Usually only metal can conduct electricity, right? Graphite is the only non-metal that can conduct electricity. All right, so between one giant layer and another giant layer, there is weak intermolecular forces of attraction. Do you remember the intermolecular? Yeah, but this intermolecular is much stronger than the carbon dioxide and hydrogen chloride and methane. Why? Because this molecule is so big. Okay, so if you look at it another way, it actually looks like this. So this is one layer. So this whole thing, I draw one layer, and then in between another layer, in between another layer. Okay, this entire layer has a few million carbon. So it's called a giant covalent structure. Get it? What is graphite used to make? Graphite is also used to make charcoal. The one you used to burn for barbecue. Okay. But it's also used to make pencil lead. You know your pencil lead can write? Okay. Why can your pencil lead write? Every time it writes, one layer of the giant covalent actually comes out. Okay. So, but then charcoal, the texture, and the pencil lead texture, same or different? Different. Who is smoother? The pencil lead, because it's added with clay. You know it's clay? It's added with clay to make it smoother. Okay. Teacher, it is called pencil lead. Does it mean it is PB? No, it's not. It's not. Then why they call it lead? I don't know. My conclusion is people are stupid. They call funny names. So I also don't know why it's called lead. Sorry, excuse me. Okay, so this is the first giant covalent structure. Okay, can? All right, the second giant covalent structure is diamond. Okay, so diamond and graphite are allotropes. Allotropes means they are all made from carbon only, but different structure. Okay, they're all made from carbon only, but different structure. So, teacher, you're telling me, right, the beautiful diamond that I want to buy, the diamond ring, that diamond, and that charcoal is actually the same? Yes. What is the difference? Can charcoal used to make diamond? Can or cannot? If can, then we all very rich already. But can or cannot? Can. In the lab, can. Okay, but this is what happens. Okay, you know how when I was teaching you that time about what ah, the fossil fuel and not fossil fuel, the carbon 14, how they find the artifacts, carbon dating that one. Okay, so many years ago, the trees, let's say the tree died. Okay, and the tree is covered and covered and covered and covered. Okay, because there is no oxygen inside there and there is no water inside there, all the material inside here is made from carbon. It will eventually be compressed. Okay, it will eventually be compressed and then become black color coal. Okay, so this is what we call coke or coal. Okay, can? So if somebody wants to go and get the coke or coal, where do they get it from? Where do they get it from? From in the cave, right? So they will dig, mine and mine and mine, and they dig it from the cave. Okay, so this coal or coke is a type of fossil fuel. It has probably been left there 10 million years. Okay, so if you are living here and some tree died here 10 million years ago, you are very rich. But if you actually left this for 100 million years, aha, you actually left it for 100 million years, this will not become a cave only. This will actually become a mountain. What's wrong with this mountain? And inside this mountain, this coal will have been compressed and compressed, high pressure, high heat. This would have been compressed to become diamond. Cool, right? So if you just live another 100 million years, you'll be so rich. Okay? Can they do this compression in the lab? Yes. So that means diamond has no value. Actually, diamond has no value. Diamond, the only value to diamond is the person buying it. Gold has value, silver has value, diamond has no value actually. The only thing that makes it got value is men. Men make it got value, but actually diamond itself is valueless because there are so many diamonds in the cave. You just have to go and uh diamonds will not run out. There's so many diamonds in the cave. Okay, it's just that whether people mine or don't mine. In fact, they actually pay people to mine slowly. Okay, so what is the difference between the structure of diamond and graphite? So I taught you just now, graphite is like this, right? Layers, right? Then diamond how? So do I have one? Here. If you look at page 183. Okay, look at page 183. This is diamond. Okay. So 183, so it's slightly different. How is it different? So remember just now diamond got four bonds. Okay, so each carbon is bonded to four other carbons. Just now in graphite, how many? Three. Okay, just now in graphite, only three. Diamond, four. So it's bonded to four others. So then this carbon doesn't say, oh, I don't feel like doing anything. No, it will continue to bond with another three. So carbon, 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 like that. And then this diamond again, one here and then another three. So it will go on and on and on and on. After a few million billion, it forms one giant molecule, which is one tiny little diamond. Okay, so is it very, very hard? Yes, because it is made from many, many, many strong covalent bonds. Every single carbon is bonded with four other carbon atoms, and it goes on and on and on forever. Okay, so because of this, it has a very high melting point because there are many strong covalent bonds between all the carbon atoms. Okay, and it needs a lot of energy to break. And because it is many, 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 many strong covalent bonds, it is actually the hardest. The diamond is the hardest substance in the world. Okay, diamond is the hardest substance in the world and is used to make drills. You know what's a drill? Okay, so to drill somebody. Okay, so it's very, very hard and it does not conduct electricity. Why it doesn't conduct electricity? Because how many of its electrons are used for bonding? All four. All four used for bonding. Okay, so if diamond is very, very hard, is graphite very, very hard? No, graphite is opposite. Graphite is the giant covalent. Okay, graphite is giant covalent, but it's not hard. The reason why it's not hard is because it has layers. So look at page 182, the page before. Okay, what's wrong with this? Graphite is arranged in layers. Okay, so the layers inside the layer is strong covalent, but between the layers is weak molecular, intermolecular. So the layers can slide over each other. So it's very slippery. So you know your oil for the bicycle chain, the black oil, that one is made from graphite because it's very slippery. Okay, so it can be used to make a lubricant. All right, so this property allows pencils to be used as to make into pencils and also lubricant. Have you heard of lubricant before? Lubricant is basically the oil they put between the bicycle chain. Okay, all right. Now, just now, can diamond conduct electricity? No, diamond cannot conduct electricity. But can graphite conduct electricity? Yes, because graphite only three electrons are used for bonding. There is one free electron. So graphite can be used as an electron because it has one free electron. Okay, so diamond is very hard, graphite is soft, slippery. Diamond cannot conduct electricity, graphite can conduct electricity. Diamond has high melting point, graphite also high melting point because it still has many giant covalent bond. It's still a giant covalent structure. Okay, can you understand? Can I? Okay. Is it confusing? Do you understand? Yeah, understand? Okay. Okay. Now we're talking about the last one. Okay. The last one is called metallic. Okay, can okay. Okay, don't confuse. This is the thing. Students, a lot of my students confuse metallic with ionic. Okay, don't confuse metallic with ionic. So let's just quick recap ionic. So ionic is positive and negative. Right or not? Positive, negative, positive, negative. Okay, and it goes on and on and on. Metallic is different. Metallic is just the metal alone. Okay, so let's say if I have a piece of metal, let's say I have a piece of sodium metal. Okay, so you learned last time. Water is water particle. Wood is wood particle. So sodium is sodium particle. All right. So this whole thing will just be round, 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 round particles of sodium. Now, if we learned last time, you will say, oh, teacher, I know. Sodium atom. But actually, the sodium is not in the form of atom. Okay, let's learn why. So it is sodium, 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 like that. But what is special about metals? Okay, I give you 30 seconds. Can you try and find me what is the electron arrangement of sodium? Come on, come on. Look through your books, look through your notes from previously. What is the electron arrangement? Okay, come on. Look at your periodic table. Look at your previous periodic. You can just look at periodic table and tell me what is the electron arrangement of sodium? Ding, 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 ding. Look at your periodic table. Do you remember?
Wait, one.
281, yes. Okay. 281. Do you know why? So you know why? Yes, okay. So basically, all metal, they are, remember the outer shell electron is called what electron? Valence electron. Okay. So the outer shell is called valence electron. So basically, metals, the valence electron is only one, two, and three. Very simple. Okay. The valence electron for metals is only one, two, or three. All right. Okay. So do you remember from previously? If you have one valence electron, in order to form full outer shell, you want eight, right? So if you have one valence electron, what's the logical thing to do? Throw away one or find another seven. Throw away one. If you have two valence electron, what are you going to do? Throw away two or find another six. Throw away two. If you have five valence electron, what will you do? Throw away, sorry, you have three valence electron, what you do? Throw away three or find another five? Throw away three. So metals only form positive ions. Okay, metals only form positive ions. So because it's 281, it will the one electron will say that I'm very bored. I don't want to wait here. I want to go walking around. Bye bye. So the one electron goes out. So the sodium, because that one electron went out, it's a positive ion. But it's not a compound, It's not a compound. It's still an element. It's just that the electron is outside the atom. So all the electrons say, hey, I also want to go and play around. I also want to go to the playground. I also want to go walk around. I'm very bored. So all the sodium is positive. And the electron, all of them is walking around freely. Okay, but when they want to react, hey, come home, and then they will come home. It's like you all go swimming, go downstairs swimming. Did you leave the condo? Of course. Okay, you're still in the apartment. So when your mother scream, come home for dinner, you can come home. So the same thing. They're just walking around the same area. They haven't left yet. So it's still an element. So what happens is in an ionic, it's a lattice arrangement of alternating positive and negative ions. In a metallic, it is a lattice arrangement of positively charged metal ions. Can you see the difference? It's almost the same. Okay? Positively charged metal ions. All right? Then what happens is the electron is freely moving. That means it can go anywhere it wants. So it has so it's called a delocalized electron. Or if you cannot remember the word delocalized, you can just say free electron. So because all the electrons are free, they are called a sea of electrons. Okay? All right? So they can move freely between the positive metal ions and act like a sea of electrons. So because you have free moving electrons, do you think you can conduct electricity? Yes, no? Yes. It can conduct electricity because the electrons are freely moving. Okay, okay. So this is the definition of a metallic bond. Okay, it's strong forces of attraction between positive metal ions and the delocalized electrons. Okay, what is the name of the attractive forces? Electrostatic. The forces of attraction are known as electrostatic forces of attraction. Okay, electrostatic. Okay, so because of that, because of this electrostatic force of attraction, the ionic bond, I hope you remember, what is the name of the attractive forces between the ionic bond? Is it also electrostatic? Yes, it's also electrostatic, but it's between positive and negative ions. This one is between positive ions and negative electrons, so it's different. Okay, okay. So because it has the free electrons, it can conduct electricity. It can conduct electricity when it's solid. Because the electrons are always freely moving. But the ionic compound can only conduct in molten or aqueous. Okay, can? Okay. You all okay? Can? Okay, please look at page 185. Okay, so most metals have high melting point and boiling point. Why? Because they have strong electrostatic force of attraction between positive metal ions and the negative delocalized electrons. Okay, so they are strong, also electrostatic, and it's very strong. Okay, metals are good properties, can conduct electricity and heat because the electrons are freely moving. All right. Okay. All metals are malleable. Okay. All metals are malleable. What does malleable mean? Malleable means when you knock them, they can be hammered into shape. Okay. So the atoms are arranged in layers and they can slide over each other. Okay. So meaning, right, these are the atoms, or you can call them ions, doesn't matter. When you take a hammer, okay, that doesn't look like a hammer. When you take a hammer and you knock it, the layers can move apart like that, can move like this, can slide over each other. Can you understand? Okay. So that's called malleable, okay, like this. Okay. So malleable means you knock, it will change shape. What is ductile? Ductile means you can make into electrical wires. This one, right, inside here, all the phone charger, everything is a metal wire. It's covered with the insulator. So how come can pull into a wire? Because it's ductile. All right? Okay? Okay, that's all for this chapter. Okay? Ding, 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 ding. Okay, so what we're going to do is wow, this is a very long chapter, right? Okay, so we have done chapter 1 and chapter 2. Okay, we have done chapter 1 and chapter 2. What I'm going to do is I'm going to do a quick review of chapter 1, chapter 2, and then next week we start bio. Okay? Okay? And then after we do 2 chapters of bio, then we do 2 chapters of physics. We see how many chapters they have. Okay, is that okay? Okay? Alright, when you go back to school, and then if your teacher is doing another chapter that you really need me to do, then you just let me know. Then we will adjust accordingly. All right. Okay. I give you 5 minutes. Read through this chapter first. We go through. We do this chapter first. Okay. We do review of this chapter first. Okay. Read through this chapter first, and then I'm going to give you some questions to do, and we'll discuss together. Okay. Why the other two boys don't come? Jeff and Jeffrey and the other one. Joakim, I'm sending you this uh document, okay? We're gonna do it together. Okay, I'll print out for you all here. Alright. So look at this. Wait, oh my goodness. One was shh. All right. So let's look at this one, the paper that I just gave you. Okay. So this is basically a summary of this entire chapter lah. Right or not? Group one, group two, group three. Okay. Okay. Now I'm gonna ask you one mistake that I made that I told you have to be very careful. Who can tell me? Very big mistake I made. And it's in pink. In IGCSE, if you're talking about group one, group two, group three, you have to write Roman numbers. Because if you're writing normal numbers, right, it is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until 18. So it's actually 1, 2, 3, 4 like that. 5, 6, 7, 8. Okay, so please take note of this. If they write like that, 1, 2, 3, right, the numbers actually go all the way to 18. It's not wrong. It's two different ways of doing it. Okay, it's two different ways of doing the periodic table. So those who write 1, 2, 3 until 18, they include the transition metals in between. And the transition metals also got numbers. What we do is transition metal got no numbers. So it's the same thing. Because you don't learn transition metal, put number for what? So in that case, if what happens if you learn transition metal, then they call it 3A, 3B, 3C or something like that. They call it some other name. Okay? So valence electron is the electron on the outer shell, right? Group 1, 1, group 2, 2, group 3, 3, duh, right? Group 4, 5, 6, 7, 8, 9. But then charge, remember only positive 1, positive 2, positive 3, they form ions. Group 5 is negative 3, negative 2, negative 1. And hydrogen forms a positive bond, but we don't use it now in this chapter. Okay? Covalent bond? No, it doesn't form covalent bond. But group 4 has 4 bonds. Group 5, 3 bonds. Group 6, 2 bonds, group 7, 1 bond, group 8, no bonds, and group hydrogen is 1 bond. Okay, remember the difference? Yes, huh? Okay, so this is basically something that you can use lah. Okay, can you please try and do question 2, 3, 4 right here? Okay, can basically the paper lah. This is everything that we just learned. Is it a lot? Is it 3 pages, 2 pages only, right? 3 pages. It's just 3 pages. Okay. You can refer, okay? I'm not gonna scream at you if you refer to your paper. You can just refer to your book or your notes and then try and do this. Okay. So today we just recap this one and we do slightly harder topics, okay? Yeah. So this one, when you want to do this, right? Don't make the mistake. Okay. So you need to do 2881 becomes 288. So you need to draw the 8. Okay? So please be sure when you're doing it. Where's positive 1? Okay, so this one same thing. I missed the one on top. Okay, wait. Okay, you don't need to write 1. You can just write positive. Okay, so oxygen is originally 2, 6. So 1, 2, 3, 4, 5, 6. It receives 1 from each of them. So 2 negative. Okay? Got it correct now? Okay? Okay. Chlorine from 287 becomes 288. You must be very, very careful what you draw. Okay. 1, 2, 3, 4, 5, 6, 7, the 8th one. Okay. So this one, why do you need to draw one more? Because it was 2882, became 288. You're supposed to draw the 8. Right not? Okay. And then this one. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Get it? Get? Alright? Okay. This one's a little bit different. This one I haven't taught you actually. Carbon dioxide, each carbon has 4 bonds. Each oxygen has 2 bonds. So this is actually called a double bond. A double bond is when you share 2 pairs of electrons. Okay? So oxygen 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then carbon 2, 4, you only draw 4. 1, 2, 3, 4. So please check carefully. Check carefully, make sure your answer is correct. Ready? Understand? Wait for Kaden to draw. Okay. Okay. All right. Looks good. Yeah. Okay, this one is from the first chapter. Relative charge is 0, positive 1, 1, 1. Okay, relative mass. It's not very easy. Okay. All right. Electrons, so if this one is 20 protons, positive 2 means it's less by 2. Okay. This one, neutron is 19 minus 9 is 10. Okay, and this one you look at the electron arrangement, proton number, this is oxygen. So you put O. Okay. The neutrons is 9. So 9 plus 8 is 17. And this one is 10, but you still write 8 because proton number. So now it's 10 is 2 minus. Okay. Do you get it correct? Okay. Ionic is positive and negative ions. Electrical conductivity is poor. In liquid is good. Example, sodium chloride. Okay. This one macromolecule is actually giant covalent. But the one I taught you was only diamond and graphite, right? So this one, if it's two elements, okay, the third one I'm going to teach you, two different elements in a giant covalent structure. It's actually giant covalent structure. So this one is called, it's actually called silicon 4 oxide. I'm going to teach you now. 4 oxide, SiO2, which is actually sand. So its silicon has four bonds. It's bonded to four oxygen. Okay, but oxygen only two bonds, like that. So does it look the same like diamond? Yeah, it's actually the same as diamond, except it's same structure as diamond, except it's a compound. It's silicon and oxygen. Okay? Okay, so it's also tetrahedral, it's also shape, same as diamond. Okay, so metallic is a good conductor in any, so it is a positive metal ions, or you can just say positive ions, and C of mobile electrons or free electrons or delocalized electrons. Okay. Okay. Are you guys done? Okay. Okay. This one is a little bit different. Okay. Now, this is a simple molecule. This is ionic. Okay, please write that down. Okay. Okay, what type of bonding is between the atoms of tetra? So this is a simple molecule, but carbon with this. Okay, what is this called? Covalent. Okay, type of structure is giant ionic lattice. Because they're not asking bonding only, they're asking structure. Okay, so this one is a little bit harder to explain. Okay, so you see, remember what I taught you? This one, simple molecule, right? Okay, and then between this and the next molecule, okay, what is the attractive forces between these two molecules? Intermolecular forces of attraction. So is it strong or is it weak? It's weak. Okay, so it's easily separated. But in the ionic, okay, lead to fluoride, Does it finish or does it go on and on? On and on. It's a giant ionic lattice. Okay. So how do you explain it in words? Okay. So there's only three things that you need to write. So CH for are simple molecules. So there is there is weak intermolecular forces of attraction between molecules. But the third one is lead 2 fluoride has strong ionic bonds. Okay. Okay. I think you guys are still not very sure at this. So I'll do this again next week. We will go through again lah. No, because you haven't started your year 9 yet, so I'm not in any rush. Okay? Okay? So we will go through the first two chapters first. We'll go through again. Now, um, we done? Okay? Okay. Alright, this one. So let's look back. So from the start, what I taught you was, so please go home and study. Next week, we will do something like a quiz. Okay, we will do first and then we'll see what you still don't understand. So we started chapter 1 was diffusion. Still remember diffusion? Remember all the concepts of diffusion? Yes? Okay, and then chapter 2, we started with the atomic structure. So we learn about proton, neutron, electron, what is the structure of the atom, and I taught you the electron arrangements. Remember? Okay, and then after that, we talked about isotopes. Do you remember what's isotopes? Okay, and then we talked about how to write down all the electron arrangements and electron configuration here. Okay, so make sure you know this thoroughly. Please go home and study. All right, and then we talked about how they are connected to each other. Okay, we talked about isotopes. All right, and then after that we did ionic bonding, covalent bonding, and today we did giant covalent and metallic. Okay, 10. All right, so we have done chapter 1 and 2, but I think maybe you are not very familiar with the questions. Okay, so I will recap again next week. We will do some more questions next week. Any questions? Any questions? No. Please study, okay? Study, okay? All right, then I'll see you all next week. Okay, bye-bye. See you on Tuesday lah. Bye.